Okay, so here we are calculating a bunch of limits from a graph. I would recommend just for help with this, see the lecture video on this. I'm not going to go through, like maybe we'll do one here. So I want the limit as x approaches -4. So that right there says -4. And that little minus there means you're coming from the negative direction, or in other words, from the left-hand side. So I'm looking right here at -4. And this little negative here says use numbers a little bit below -4. So I'm using this little chunk of the graph. What are my y values approaching as I'm getting closer to -4? My y values are getting closer to 2. All of our answers here are the y values as we approach a certain x value. So the answer to this first part is 2. Okay, now, like the rest of these should be pretty easy. Places where the limit doesn't exist. How can a limit not exist if either of the one-sided limits doesn't exist or if the one-sided limits don't agree? Now, this one is tricky. Places where the function's not continuous on its domain. Now, different books define continuity of a function differently. The definition I like is to say that a function is a continuous function if it is continuous everywhere on its domain. The reason that's a good definition of continuity is all polynomials then are continuous functions. All rational functions are continuous functions. Consider the function f of x equals 1 over x. We learned this back in college algebra. We're not allowed to divide by 0, so the domain is all real numbers except 0. 0 is not in the domain of this function. Every other real number is in the domain of the function. Under my definition of continuity, we would say this is a continuous function. Can you draw it without picking up your pencil? No, we've got this vertical asymptote right here at 0. You can't draw, these pieces aren't even connected. What do we mean continuous? We mean continuous everywhere where the function is defined. Every real number except 0, this function is continuous. So that's a very convenient definition of continuity of an entire function, because under that definition, any function that you can write down in a single line, no matter how complicated it is, if you can write it down in one single line, meaning you're not doing a piecewise function, you're just writing down a formula, that function is continuous. Guaranteed. Every function you can possibly imagine and write down is a continuous function on its domain. So that's a very convenient definition of a continuous function. It's continuous if it's continuous everywhere where it's even defined. So yes, this function is not continuous at 0. It doesn't even exist at 0. But it's still a continuous function. It's tricky. So in this question here, I'm being very explicit. I want you to list every place where the function is not continuous, but I only want you to list ones that are in the domain. If a number is not even in the domain, if the function is not defined there, if there is a place where there is no solid dot up or down above some x value, we don't even consider it to answer this particular question. Sure, the function might not be continuous there, but I'm not asking about those. I'm only asking about x values that are in the domain. So be careful with this. It's kind of a tricky question.